Alright, so in this video, we're just going to quickly go over what we know about our parametric arc length and surface area. Okay, this will be video 6 of our parametric and polar review. So we have our two equations here, x equals 5 cosine t and y equals 5 sine t. We're trying to find the arc length, okay? We're trying to find the arc length of that whole entire curve. Now, that would mean that we would need to integrate from 0 to 2 pi, right? That's the whole curve. We know that 5 cosine t and 5 sine t, that's going to make a circle. So we integrate from 0 to 2 pi, and what are we integrating? Like, what's our formula here? Well, it's going to be dx dt squared plus dy dt squared dt. So the first things that we're going to need to find is dx dt and dy dt. We're doing that real quick. Dx dt, we know that that's going to be negative 5 sine t. And dy dt, well, that will be just 5 cosine t. And like I said, we know our bounds are from 0 to 2 pi because the graph 5 cosine t, 5 sine t is just going to look like this. It's going to be a circle. Okay, so we have to integrate from 0 to 2 pi. Okay. Now, we can plug this in. We get the integral from 0 to 2 pi. The square root of it's going to be dx dt squared. Okay, so we get 25 sine squared t. We get plus 25 cosine squared t, right? That's going to be that squared. And then we get a dt on the end. We can factor out a 25, which will give us a 5 on the outside of the integral. 5, the integral from 0 to 2 pi of, now we're just left with that sine squared t plus cosine squared t in the radical. And this makes it very easy. Note this will not always happen at all. Okay, I just want to do a quick and dirty example so you kind of get the idea of what we're doing. Okay, you get a little quick refresher. Okay, 5 times 2 pi, that's going to be just 10 pi. And then 0 kills everything off. So that right there is your arc length. For this problem, it's really nice. We can actually check our work here. Okay, because we know the area, or not the area, the arc length is the circumference, and that's 2 pi r. We have a circle that has a radius of 5, right? That's the 5s here. Okay, and that will give us 10 pi for our circumference. So you can kind of check it there. Now, what else could you see here? I mean, you might end up with some kind of inverse trig substitution that you have to do, but really, I mean, it's not going to be too bad because then it would take you too long to do on a test. Okay, so don't freak out and think that you're gonna have to take 25 minutes on one problem. All right, that's not really what's. Now, what if we wanted to find the surface area of these two equations rotated around the x-axis? Okay, so if they're rotated around the x-axis, let's say that right up here. Now we want to find the surface area of this solid that we just created by rotating these two curves around the x-axis. Okay, well here, I mean, remember, we do have that graph. I erased it, but we still have that graph that we create. Okay, but if we're rotating it about the x-axis, we really don't need to worry about that, the everything below the x-axis, because it'll get covered when we rotate it all around. Okay, so we only have to really integrate from 0 to pi. All right, integrate from 0 to pi. All right, just think, right? It's that piece that was there. Okay, when we rotate around, that's just going to get covered by what we're rotating around. So yeah, we don't need it there. We can integrate from 0 to pi. Call it good. Now, we get 2 pi y. This y is here because we're rotating about the x-axis. If we were rotating about the y-axis, then we're going to have an x here. Okay? We're going to get a 2 pi times y, that is 5 sine t. Cool. And now we are going to be multiplying by the square root of dx dt squared plus dy dt squared. And we had that for the last problem, so it's going to be 25 sine squared t plus 25 cosine squared t dt. Now we can take out a 5 that we get from the radical. We can get that 5 out from the sine t. We get that 2 pi out. And we're going to end up with a 50 pi out here. The integral from 0 to pi of sine t. And what's left with this radical is just going to be sine squared t plus cosine squared t. That's 1. So we just get a sine t dt. Integrating this, you get 50 pi times, this will be a negative cosine t, so we can just pull out that negative cosine of t evaluated from 0 to pi. Doing our little evaluation here, negative 50 times cosine of pi minus cosine of 0. And we know that that is negative 50 times a negative 1 minus 1, right? Cosine of pi is negative 1. Cosine of 0, that's 1. And we get a negative 50 times negative 2. And where did my pi go? There it is. Forgot it. So that's going to give us 100 pi. So, what is the surface area for a sphere in general? Because that's what we get when we rotate this around the x-axis. Well, that's 4 pi r squared. Okay? And, well, let's plug that, our radius, we know that's 5, right? So, if we plug that in, 4 pi times 5 squared, we get surface area is equal to 100 pi. So another cool way to check your work right there, but that's only because we had something really nice like a sphere. Okay, anything else that you would get from this? I mean, you might have to do some sort of u substitution. I don't think you'll have to do integration by parts, but that might pop up. I don't think about any inverse trig substitution. That probably won't. It'll probably just be a u substitution that you'll have to do. But yeah, it's not going to be anything too bad. Definitely, if there's going to be something that's hard, it'll be the arc length problems without a doubt, because they don't have this little nice like y or x out there. Okay, so that's going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for parametric and polar in the next video in the series. See you soon.